Okay, let me say something about these two problems. It's 11.3.4, 11.3.5 in the old version. The new version will have a different numbering. So these problems refer to some real valued functions. In particular, this function c of x defined as e to the x for x in the real numbers. So problem A says, given that the domain of C is all real numbers, what is the range of C? Right. So here I didn't really ask for a proof. I suggest if you don't know the answer, you can graph and see what values this function takes. In part B, you need to prove that C is a bijection between its domain and its range. All right. So remember, bijection is one-to-one and onto. Now, a function is onto its range by definition. So it's onto by definition. Right? The range is the set, subset of the codomain for which the function assumes those values. So it's onto by definition, but you need to prove that it's one-to-one. And one way you can do that is you can use the fact that it's increasing function. That's one way. The exponential function is an increasing function. All right, so part C. Find group operations on the domain and range of C such that C of x preserves operations. That is, C of x dot y equals C of x circle C of y, where dot and circle are the group operations of the domain and range respectively. So verify that C does indeed preserve operations for these preserve operations for these two operations. So what you want to do is you have two sets now. You have the domain and the range. And you want to define a group operation on the domain and a group operation on the range, and ensure that when you use this function, c of x equals e to the x, that this equation works. That the c of x, and this is the group operation on the domain with y, and then that should be equal to c of x, and this is the group operation on the range. So that's a equation. It's a substitution here, right? You have to substitute the function, what c is, and you need to substitute what this operation is, and then show that this equation works when we also substitute the operation on the range in here. All right. So this last question ties these all together, that these three parts do tell you something about these two groups, the additive groups, the multiplicative group on the positive real numbers and the additive group on all real numbers. So you're supposed to draw a conclusion about these two groups based on these three parts. All right, now the next problem is related. So first we're asking a similar question about domain and range. What's the largest possible domain and range of the natural logarithm function ln of x? So we'll only consider real valued logarithms and not logarithms of complex numbers or complex valued logarithms. So just the conventional real valued logarithm function that you saw in high school. But I want the domain and the range. All right. So part B, using results in relation between natural logarithm and exponential functions, okay, as well as a result from earlier in this chapter, show that the natural logarithm function is an isomorphism. And what are the two isomorphic groups? All right, so you want to kind of leverage what you showed in the earlier exercise to show that natural logarithm is also an isomorphism. Okay, using the fact that log 10x equals log x over log 10, show that the base 10 logarithm is also an isomorphism. What are the two isomorphic groups? Now you can consider this function log 10 of x. I can consider that as 1 over log 10 times log of x. Whoops, log of x. Now this is actually a composition of two functions. It's a composition of two functions. I can take f1 of x equals log of x, and I can take f2 of x is equal to 1 over ln 10 times x. And then you can verify that log 10x equals f2 composed f1 of x. And then you can use some earlier results about the composition of isomorphisms. Okay? So that's all I'll say about that. All right, now, given any two positive real numbers, a and b, in scientific notation that are accurate to 3 decimal places, show how you may estimate AB using addition and a table containing the logarithms of all integers. So I should say the base 10 logarithms here, of all integers from 100 to 999. Okay, so for instance, I should be able to do 1.23 times 10 to the 5th times 3.67 times 10 to the minus 12. All right. So how are you going to use the table of base 10 logarithms to compute this product? And you're going to be using the isomorphism property to do that. Okay, so that's all I want to say about those two problems.